Okay, so I'm going to spend the next hour, the first hour here, talking about some of the 207 specific topics, focus on that. Then I'm going to head into the 250B stuff, and I'm going to do the stuff first today that I did not do yesterday, because we got cut short yesterday by this power outage, and so I didn't really get to do a full review session yesterday for anybody. Like I had intended. So let me tell you sort of there are 4 topics in 207 that are not sort of in the 250B realm that I think you should be ready to answer questions about. So let me make a list of those topics, and then we're just going to do an example of each one. So orthogonal trajectories. This was an application of differential equations that we started off with right at the very beginning. And then there was Euler's method. This is for numerical approximations to differential equations, initial value problems specifically. This is best done with a calculator, so I'm going to, contrary to what I probably said before or what I wrote down, I'm going to let you guys bring a non-graphing calculator on Wednesday. So you generally would want that. All you need is like a basic calculator. You could check one out of the math office if you wanted, but if you don't have one, I would suggest you do that way in advance of the exam. In case they don't have one, then you have another opportunity to make another plan. So a non-graphing calculator, we'll review all of these things in a little bit. Then there's the LU factorization of a matrix, sometimes called LU decomposition. And then finally, the last thing is sort of more of a generic thing, which is proofs of abstract vector space properties. Okay? So these are the topics that we did in Math 207 that we didn't do so much of in my 250B class. So I want to do these first. In exchange for this, you guys don't have to do anything from Chapter 5. So if you're sticking around for the 250B review, anything that's about Chapter 5, which is inner product spaces, we did not cover in 250B because you're going to see it, sorry, in 207. We did not cover it in 207 because you're going to cover it in 307, right? I'm going to do that stuff at the very end of my 250B review so that if you want to stick around to hear some of the other stuff that's common with 250B, you won't be wasting your time listening to me talk about the stuff that you don't need to know. So that's kind of the way I'm trying to organize this as best as I can. So let's just talk through a few examples of some things here. Actually, the first one is out of the book, so let me, I just want to do a couple of examples to get this back into your mind. And you're not going to find this, so for example, if you look at the sample final that I posted, it's really just an old 250B final, so what you need to realize is that none of these topics are going to be appearing in there. And also there will be some questions in there that are from Chapter 5, which you can skip, right? So it's not perfect. I don't have an actual, since I've never taught 207 before, I don't have a former exam from 207, but I'm hoping that there's a lot of overlap, like probably 80 to 90% overlap, so I figured it was worth it to put that up for you. But so some of these problems are just, I'm just picking them out of the book. You can also go back to, I'm just going to call this example A. You can also go back to the first midterm and the second midterm. The third midterm was completely the same as 250B, but the first 2 midterms there were differences in terms of the actual topics because this stuff was from the first 2 midterms. Okay, so let me talk about orthogonal trajectories. I'm going to give you the following problem. So consider the family of curves. So here's the equation, x squared plus 3y squared equals 2cy. Okay, and the question is going to be to determine determine the orthogonal trajectories to this family. Okay. Does anybody know what, just out of curiosity, this isn't really the main point of the problem, but does anybody know what this family of curves looks like? Yeah, if it was just x squared plus y squared, it looks like a circle, but the 3 in front of it makes it more elliptical. And the fact that this is equal to something that has a y in it, see, you could actually do completing the square process if you subtracted the 2cy to the other side. What that would do is shift the center of the ellipse up and down the y-axis. So x is centered at 0, but the y component of the ellipse will be centered at different points depending on what c is, right? So this is just a family of ellipses that are kind of staggered up and down the y-axis. And they're asking us to determine the orthogonal trajectory. So remember, orthogonal means perpendicular, right angles, and if you're talking about the slope of two curves being off by 90 degrees from each other, right? So forming right angles, the slope relationship between the two curves is negative reciprocals. So if one line has a slope of, you know, I don't know, m, then the perpendicular line has a slope of negative 1 over m. So the way to do a problem like this is going to be 3 steps. First of all, figure out what's the slope of this family, then take the negative reciprocal of that and use that to create a differential equation for this family, right? And then the third step is to solve that differential equation. Okay, so let me just write that down. So 3 steps to do a problem like this, right? The first step is find the slope m of the original family that's given, right? So that's the given family. And then the second step is to set up a DE with the slope, which is dy over dx, equals to negative 1 over m. So that's the negative reciprocal of the slope of the original family. And then the third step is going to be to solve the DE. So this is going to be the approach here. Okay. So far, so good. Okay, so let's start with the top. So again, here's the overview. We're just going to try. I'm going to see if within an hour I can do one example of each of these things. I think I should be able to. So the slope of this original family. So in other words, I need to know what is y prime for this family. And how do you suggest that I do that step? Anybody have an idea? Yeah, just take the derivative of both sides with respect to x. That's exactly right. So I'm going to do d dx of the left side, right? And that has to equal d dx of the right side. Okay, so that's the idea. So I just simply differentiate here. The derivative of x squared is 2x. The derivative of 3y squared is 6y times y prime, because you're differentiating with respect to x here. So this is actually the chain rule. Right, so the derivative of 3y squared is 6y times y prime. And then on the right side, when I differentiate with respect to x, I just get 2c y prime. 2c is a constant. Okay? So I should be able to group the y primes together. That's going to be the idea here. So let's see, how's that going to look? I'm going to just put the y prime terms on the right side of the equation. So I'll subtract the 6y times y prime term to the right side. And so then I get y prime is equal to 2x over 2c minus 6y. And we can actually replace c. So one more thing we need to do here. We can replace c by using this equation to replace it in terms of x and y again. So let me just show that right here. So if we actually were to solve this for c, it would be x squared plus 3y squared all over 2y. Right? So that's going to be the formula there. Does this make sense so far? So I'm going to put that in for the c right here. So maybe I'll just work over on this side now. So I have 2x over 2 times, well, c is x squared plus 3y squared all over 2y minus 6y. Looks a little messy, but hopefully it won't be too bad. I'm going to cancel the 2 with the 2 right there. And then I'm actually going to split up that denominator. So this is x squared over y. And then notice what's going to happen. I'm going to get plus 3y, but then minus 6y. So that adds up to a net total of minus 3y. And if I make a common denominator of y right here, that means I write it as 3y squared over y. I can then flip the y up to the top. So I can do that, and I end up with 2xy over x squared minus 3y squared. So this is my differential equation. This is the differential equation for this is the slope, in other words, of all of these ellipses at any point xy. Clear enough? Great. So the slope, so that's step 1. Step 2 is where we need to now set up a differential equation for the orthogonal trajectories. So all you have to do for that is take the negative reciprocal of what you just did in step 1. So if you do that, you're going to take the reciprocal and take a minus sign. I'm going to rewrite the subtraction in the opposite order here to make that happen. This is the equation you end up with. So this is the differential equation for the orthogonal trajectories. That's step 2. Just basically write it down. By the way, is everybody with me? We have a family of ellipses that are staggering up and down the y-axis, and we're trying to find the orthogonal trajectories to that family of ellipses. So to do that, we figured out what the slope of the ellipses was at any point xy, and we said the orthogonal trajectories would have a slope of negative 1 over the slope of the original family. So we just took the negative reciprocal of what we had gotten right here. Whatever we got right here, we took the negative reciprocal of it and put it right there. And now we're ready for step 3, which is to solve the differential equation. How do we solve this differential equation? Exactly. It is a first order differential equation, and it is homogeneous. It is homogeneous. Do you notice if you attach, remember, so this is a good review of section 1.8. If you attach t's to every single x and every single y that's on the top and on the bottom, the t's all just cancel right back out again. Exactly. So this is homogeneous. And so do you guys remember how to solve a homogeneous differential equation? Y equals xv. Very good. Exactly right. Y equals xv. And the derivative of that by the product rule is just xv prime plus v. Okay, great. So what we would do then is plug everything in terms of x and v. So the y prime, if we incorporate that, the y prime becomes xv prime plus v. And on the right side of the equation, we have 3x squared v squared minus x squared all over 2x squared v. So I hope I did that right. Okay. And all of the x squareds cancel on the right side of this, so you can replace this with 3v squared minus 1 all over 2v. There we go. Or in other words, I'm going to simplify this a little bit more. This is 3/2 of v minus 1/2 of 1 over v. Okay, so 3/2 v minus 1/2 of 1 over v. Now I'm going to subtract the v to the other side. So remember, the left side is right here. xv prime plus v equals all of this. I'm going to use this v to cancel with the 3/2 v. And it's going to leave me with just xv prime equals 1/2 v minus 1/2 of 1 over v. And so this is what you're going to get. Are people with me so far? It's a little different than the way I must have done it before. Oh, that's okay. It's good enough. So this is actually, if we make a common denominator of 2v, we just end up with v squared minus 1. What kind of equation does so when you have a homogeneous equation, which is what we have here, and you apply this change of variables to it right here, what kind of equation do you always end up with? Do you remember? Say again? Separable. Exactly. Homogeneous equations always become separable, and you can start to see that that's what's going to happen here, because if you rewrite the v prime as dv over dx, right, and you set this equal to v squared minus 1 over 2v, now you can put all of the v's on one side. So on the left side, I'm going to put 2v over v squared minus 1 times dv, and on the right side, I'm going to put 1 over x dx. So do you have to flip things around a little bit to get that to work? But that's what it comes out to. Okay? And once it's separated, like we have it here, the next step is to integrate on both sides. Okay, so we have to integrate both sides. On the left side, this is actually done with a, how do you do the integral here on the left? Right, u substitution, and we can let u equal v squared minus 1, and the derivative of that is right on top. So it's really the integral of du over u. And the antiderivative for that is going to be the ln of the absolute value of whatever the u was. The right-hand side has an ln of absolute value of x plus c, right? So you do have to put a plus c there on the end of that. Now we can exponentiate to get rid of the, so this is not an acceptable answer, right? We've actually done the separation part and the integration part, but we haven't actually rewritten it in terms of y yet, and we haven't really put this in the best form. Sometimes it's not possible to solve for y. If on the test I say something like, you can just give an implicit solution. If I say implicit solution, well, it means that you can leave it without solving for y. But you definitely need to get rid of the v and rewrite it using y over x. Right? Make sure you always go back to the original variables. But let me just exponentiate this on both sides, right? So e to the ln of whatever just gives you whatever, okay? And then on the other side of the equation, be careful. This plus sign is going to turn into a multiplication. E to the c becomes c1, and e to the ln absolute x just becomes absolute x. Okay, I can remove the absolute value signs from both sides of the equation if I'm willing to pay the price of a plus or minus. And as you've seen me do in class before, plus or minus of a constant is just another constant. I'm going to call it C2. So we get v squared minus 1. Oh, I'm sorry, I can get rid of these. As I said, I was going to get rid of these absolute value bars. So on both sides there's a plus or minus. So combining that all together into a plus or minus, this is what you would have left. And so now I can just, I'm just about done. Just come back over here and I just have to figure out what is y equal to. I think we can actually solve for y here, right? So v squared is equal to plus or minus c1 x plus 1. Again, c1 plus or minus c1 is just c2. So I'll just say c2 x plus 1. And now I can solve for y squared because it's equal to x squared times v squared. And so there you go. This would be almost explicitly solved for y. Y would now be plus or minus the square root of all of that. And you would be more than welcome to leave it like that. Okay, let me just make sure that's the answer that I came up with earlier. Yeah, looks great. Okay, people feel all right with that? So that's kind of how you do a problem like that. So this is the curves that provide the orthogonal trajectories to the original family of ellipses. So 3 steps. Take the original family, figure out what the slope of that family is, right? So figure out what dy dx is. That's going to involve taking a derivative. Then replace the slope that you get there with -1 over reciprocal. And then finally solve that differential equation. Actually, when we were doing these orthogonal trajectories back in chapter 1, we hadn't learned homogeneous equations yet. I think in most cases in that part of chapter 1, all we ever did was write down the differential equation for the orthogonal trajectories. We didn't know how to solve anything at that time. That was like back in the first week of the semester. So now it's kind of neat to see an example where we actually can take this new differential equation and solve it using something that we learned a little later on. Okay, so that's one of the 4 topics that is Math 207 specific. Let me give you the next one. So this clock is wrong, right? It's like 2:25 or so?
Yeah.
Okay. Okay, so let me give you the next. I think that the next topics, so the second topic might take a minute, but the LU factorization and the abstract proofs won't take very long. So we'll get this done within the first hour. I'm pretty confident. So the Euler's method, so I'm going to call this example B. So just going to do one example of each of these 4 things to kind of get it back in your mind. So here's what we're going to do. Consider the initial value problem, which is y prime equals negative of the quantity y plus 3x all over y squared. And y of 2 equals 3. So we have an initial value along with the differential equation. That's what an initial value problem is. When you have an initial value problem, the solution to that differential equation is always unique once you plug in the initial value condition. So there's a general solution here, right? There'll be a general solution here, but then this initial condition will specify the constants in that general solution, or constant, I guess, in this case. So there will only be one solution. So in a minute, I'm going to ask you to estimate what the value of that solution is at a particular point. And that will be a well-defined question. It will make sense, in other words, because there can only be one right answer. Once you have an initial value given, there's only one right answer to these problems, and so that's what this question is going to be asking for. Okay? So, so far everybody with me? By the way, I was very careful to pick something that I don't believe that this is separable. It's not linear, it's not even Bernoulli, and it's not even homogeneous. So this is not one of the 4 main types of first order differential equations that we learned how to solve. Because otherwise, if you could solve the differential equation algebraically, you wouldn't need to use Euler's method, which is what we're going to actually be using. Right? You could literally just solve the equation and then get an exact answer. But since this one is not one that we know how to solve, then we have to do something else. We're going to only be able to make an estimate. So I'm going to estimate y of 2.4, okay, where y is a solution to this initial value problem, and use step size h equals 0.1. By the way, guys, use step size h equals 0.1 in Euler's method. Oops, Euler's method. I wanted to mention, and I think I was clear about this in the review packet, I'm not going to ask you about the modified Euler's method. We did talk about a sort of a refinement of this method, which is in the same spirit of this one, but with a little bit better estimation techniques, but it's also more computationally intensive. So,
thank you.
yeah, we're just going to go with the basic one, okay? Just to make sure that everybody's had a chance to review this basic Euler's method. So yeah, so that I'm going to keep it pretty simple. So there's one thing above all other things that you need to make sure that you know to solve a problem like this, and that is the formula for getting from one iteration to the next in the Euler's method procedure. So that's the main thing. So here is the most important formula that you guys need to make sure you know. That the next y value estimate, let's say the n plus first y value estimate, comes by taking the previous y value estimate, which is y sub n, and adding, you're literally just going to add the slope times the run. So I'm going to write this as f of xn, yn. What is f here? F is just this whole thing over here, which is the slope, right? Y prime is the slope. So this is the slope of my solution curve at a particular point, which is my previous estimate. So that's the slope times the run, and the run is the h. Okay, so if you don't remember anything else about the Euler's method, this is the one thing you absolutely need to know. All right, otherwise you can't do the problem. Okay, so if you know this formula, and as I was saying, Morgan, you might not have been here right when I said it, but you can bring a non-graphing calculator. Okay, so it's just going to be sort of a plug and chug exercise. I usually like to make a little table, right? I put my n values here, right? And then I put my xn values and my yn values here. Okay? And I'm always starting off at n equals 0 with the initial condition. The initial condition is that x0 is 2 and y0 is 3. So this is coming, so from the initial condition I can fill out the first line. Okay? Now, because the step size is 0.1, that tells me how the x's are going to be spaced out, right? So that at the next iteration, which will be n equals 1, the x is going to be 2.1. And then at the one after that, 2.2. The one after that would be 2.3, and the last one would be 2.4. We can stop at 2.4 because that was the y value that we're trying to estimate. So we have to do 1, 2, 3, 4 steps. Okay, so that's, I just like to make this little table. Do you guys remember doing this? Yeah. So, we even did this one on a program at one point, a computer program. I had you guys write it up, and it was, once you have the program, it's very easy, right? Just plug in the numbers into the program, and it does all the calculations for you. So, all right. Well, the hard part is getting the the last column here. We're trying to get the number down here in the bottom right corner. So, for example, y sub 1, so I'm going to use this board for my scratch work. To figure out what y sub 1 is, I'm going to take y sub 0. In fact, let me just write it out. Y sub 0 plus f of x0, y0 times h. And let's just plug everything in that we know. Y0 is 3. We're going to do f of 2, 3 times 0.1. So I have to put in, into my function here, I have to put in x equals 2 and y equals 3. So this is 3 plus 3 times 2, that's 9, divided by 3 squared, which is 9. So this is just negative 1, right? Just negative 1, so this is actually just 3 plus negative 1 times 0.1, and that gives me 2.9, obviously. So I'm just subtracting 0.1 from 3. So that tells me my next y value, which is 2.9. Okay? So far, you don't really need a calculator to get to this point, but it's going to get messier. It always does. Okay? So for the next y value, which is y sub 2, we have to take y sub 1, which is 2.9. It's just the previous y value. And then we have to evaluate f of 2.1 comma 2.9. So there's the formula up there. It's going to be negative 2.9 plus 3 times 2.1. I'm just going to go ahead and do that in my head. 3 times 2.1 is just 6.3. And then all divided by 2.9 quantity squared. Okay, and then this is going to be times 0.1 again, right, the h value. Okay, now you need the calculator, right? It doesn't take very long until you kind of need the calculator to figure this out. So I'm going to save you the aggravation of working it out and just tell you what it is. The answer turns out to be 2.791. So we'll put that here, 2.791. Okay? So far so good? Yeah.
Approximations, do you want us to store as many decimal places?
As many as possible would be good. The more decimal places you store, the better. However, I will probably tell you like how many decimal places to save on the test, because otherwise I'm going to get slightly different answers from everybody. Yeah, so this has been rounded. Obviously, this is an exact answer. This one has been rounded, in this case, to three decimal places. Yeah, but I'll tell you. I'll be specific. If I want 3 decimal places, I'll say that. Okay, so this is just 3 decimal places. Yeah, so I'll try to be. I don't like exam questions where there's ambiguity, and I get as many different answers as I have people taking the test, and grading is a nightmare. So I'll do my best to be specific with you about that. Okay, then we just have to keep going like this. And this is not like actually heavy math. It's really just doing numerical calculations and doing them with a basic calculator. So I'm not going to spend too long on this. So for the next one, right, you take 2.791, and you would have to add that to, again, some expression that's going to get multiplied by 0.1 here. The denominator is 2.791 squared, and then on top you'll have negative of 2.791 plus 3 times 2.2, which is actually 6.6. Okay, so you get something like that, and I already worked this one out as well. This is approximately 2.670. So I worked that one out to 3 digits as well. Okay, and then finally, y sub 4 would be, 2.670. So I'll put that in the table here, 670, right? So we get that, plus, be sure to show your work, especially, I would recommend drawing this table out. Because if you don't show your work and then I just see an answer at the bottom, and if it's not right, I'm going to have a real hard time giving any kind of partial credit for this. But if I can see that you're actually plugging the right numbers in the right places and everything, then if the number didn't come out, maybe you have to be careful. Some people, they have all the right formulas on the board, but then I've seen people have trouble getting it into the calculator correctly. Like you have to know the order of operations for your calculator. So like, here, you have parentheses around this plus sign. If you don't use parentheses in your calculator, let's say you do 2.791. So if you type into your calculator something like 2.791 plus 6.6 divided by 2.971 squared, right? Your calculator is going to do that, which is not what you want. So be a little careful with that. Everybody, this isn't really a course on how to use a calculator correctly, but I've seen more mistakes with that than you might imagine. And so it's a really good idea so you really got to put parentheses here. You can have a minus there, right? Make sure that all of that is very clearly done. You can do it in pieces. If you're really not sure, just square the denominator first, write it down on your side scratch paper, then figure out the numerator, then go back and divide the 2 numbers, right? So you can do it that way too. So what am I going to have here? Negative of 2.670 plus 6.9 all over 2.670 squared. And that comes out, I've already worked this out ahead of time, it's approximately 2.536. So if I asked for 3 decimal places, this is what you would give as an answer. Okay? Does everybody remember this more or less? The modified Euler's method is more complicated. You have a y star, like this extra point that you kind of use as a better estimate for the plugging into the function for the next iteration, and you get a better estimate, but it's also a lot more work. Do you have a question?
Yes. Are you gonna write on the test use Euler's method, or are we gonna have to recognize that we need to use it?
I will have to ask you that because otherwise if I just say here's what H is and here's a initial value problem, you're gonna be like, I don't really know what that's supposed to refer to. Yeah. So you'll be able to recognize this problem really easily if I give you one. Yeah, the biggest thing is really just making sure you don't screw things up with the calculator. So a lot of times that's where the main problem goes or lies. Does anybody have any other questions on this example? Okay, if not, let's go on to the third of the 4 topics, which is the LU factorization of a matrix. This is also something that I didn't cover in 250B, but that I did cover for you guys. And I think it's a good topic for math majors to be aware of. So I have an example for this also. Find it here. Here we go. So example. Write the LU factorization for the matrix capital A equals, so I have a matrix here, is going to be 2, 4, -4, 0, 1, 3, 5, 2, 6, -9, -15, 3, and 2, 7, 3, and 1. Okay, this is a topic that is only for square matrices. And the goal of this is to, well, what we're going to do is we're going to write this as a product of a lower triangular matrix and an upper triangular matrix. You will always be able to do that provided that the only EROs that you perform are the AIJ operations. So we're not going to multiply rows through by constants here. We're not going to permute 2 rows. So if you see a question on the test, write the LU factorization of a matrix, you need to be thinking, okay, I'm only going to do the AIJ operation. I'm not going to get 1s in the pivot positions or anything like that. I'm not going to switch the order of anything. After all, this upper triangular matrix does not have to have 1s on the diagonal. So I'm perfectly okay with starting off with a 2 here and living with it that way. Okay, so we can just leave that part alone. We're just going to do only the AIJ operations. Okay, so the way that you solve this, just to remind you, is you just do EROs on the matrix. And I know that sort of towards the end of the semester, I got a little bit casual about writing down which EROs you were doing. We started just crossing off rows and doing things kind of quickly and multi-steps at a time. For this, it's really a good idea to go back to that more disciplined approach, because when you're writing down the lower triangular matrix, you need to know what numbers to put into it, and those numbers come from these operations here. You kind of remember this? I'm going to remind you. So that's why you need to be careful here. It's not that I'm trying to go back to being, fussy again. It's just that for you to get this problem right, you really have to keep track of it. So for example, what I would probably do here is I would just do A12, A13, and A14. I can do all of those together. These are the operations that I'm allowed to use. So for A12, what multiplier would you want me to use? -1/2, right? Because if you take -1/2 times 2 and you add it to 1, you'll get a 0 there, right? And how about the A13 multiplier? What would I use for that one? -3, very good. And then for the A14 multiplier? Just -1, exactly. Okay, so there we go. So let's do all of that at once, okay? The first row stays the same. All right, I'm going to take -1/2 times the first row and add it to the second row. So I'm going to get a 0 here, and we get a 1. -1/2 of -4 is 2 plus 5 is 7, and then the last entry is still going to be a 2. Okay. Now I'm going to take -3 times the first row and add it to the third row. So I'll get 0, -23, I believe. No. I'm sorry, -21. -21, right? So, and then I get -3. 3, and then 3 again. Is everybody with me on this? Stop me if I'm going too fast. I'm just doing all these EROs. And I'm going to take the negative of the first row and add it to the last row. So 0, 3, 7, and 1. Okay? So far, does that look okay? Okay, we're going to keep track of these numbers here. We're not going to use them quite yet. I just want to get the, what we're looking for here is the triangular form. So you don't need to worry about any of this stuff because this is for my other class until
3 o'clock or something.
exactly.
Okay.
Yeah. So I just came in early to help these guys with some stuff that is not part of your test. Okay. So you can just tune me out.
All right.
It's the one time you're allowed to do that. Okay. So so now I have to keep going. I've got to get. I'm basically trying to get this into a triangular form, right? So I'm going to use what should I use here? A 2, 3 of 21 and a
2, 4 of
right, a 2, 4 of negative 3. Okay, good. So the first 2 rows are going to stay the same. First 2 rows are exactly the same as before. Now I'm going to take 21 times the second row and add it to the third row. I'm going to get 0, 0. Is that right? 18? No. Let's see. 21 times 7, right?
Yeah, that's.
Oh gosh, that's 147. And I subtract 3 from that, but 144. I didn't say the numbers would be nice. And then 21 times 2 is 42. I have to add 3 to that, I get 45. Okay. And finally, finally a 2, 4 of negative 3. I'm going to get 0 and 0. Negative 3 times 7, add to this is negative 14. And negative 3 times 2 is negative 6. I add 1 to that, I get negative 5. Okay. We're not quite into upper triangular form yet, so I have to do one more step to get that. And that is, I'm going to leave the first row the same, the second row the same, and the third row the same. So the first 3 rows are not going to change, but I have to zero out this negative 14. So I'm going to use A3, 4. I have to take some multiple of the third row and add it to the fourth row. How about 14 over 144? Okay, that gives me a 0, a 0, and a 0, which is what I need. And then you have to figure out what number. So you have to take, okay, I'm going to do this for you. You have to take 45 times 14, divide it by 144, and then add that to negative 5. The answer comes out to negative 5/8. Okay, guys, I threw this problem together quickly for the review. Probably for an exam, I make the numbers a little nicer. But for the review session, I'm just like, okay, that works, let's just go with it. So, anyway, so just take my word. Actually, and if you got this number wrong, but you did the whole entire problem correctly, I would take off the absolute most minuscule points, if anything that I could. I might not even take off anything, as long as I see that you're doing the right approach. So, now, this matrix that you get at this point where we have done only these A operations, this is the U matrix. I just remind you, that is the upper triangular matrix that you've been looking for. You don't have to do anything else to it, right? It's not going to be necessarily ones down the diagonal, but that's fine. Okay, now to get the L matrix, which is the other part of this, what we have to do is create some space first. Write it down. Actually, if we've done a good job of our bookkeeping here, we can just write it down as well. We don't actually have to work very hard. For the L matrix, this is a lower triangular matrix. The one thing about this matrix is it will actually be unit lower triangular, so I can already fill in half of the matrix like that. It's going to have ones on the main diagonal, zeros above the diagonal, and the lower triangular entries are down here. And there are 1, 2, 3, 4, 5, 6 more entries to put in. And notice that there are 1, 2, 3, 4, 5, 6 numbers that we have used as multipliers. And what you have to do is take the, okay, this is very important. You have to take the negatives of these multipliers and put them in the corresponding position. So like here is 1, 2. It becomes the 2, 1 position right here. And I take negative a half and I change it to 1/2. Okay, so 1, 3, whatever the A13 multiplier is going to be put in the 3, 1 position, and I change the -3 to a +3. And then finally the -1 changes to a +1. So literally this becomes the first column. The negatives of these multipliers are the first column of L. The negatives of these multipliers are the second column of L, so I'm going to get -21 and +3. And then the negative of this multiplier, which is negative whatever, -14 over 144 becomes the multiplier right there. Okay? So when I say write the LU factorization, I really just mean tell me what L is, tell me what U is. What you can do is check that your answer is right by multiplying it out. So you could figure out, well, what is L times U? This would take you a little slight bit of time. You're going to put the L right there, and you're going to put the U right there, and just multiply it out. You should get the original matrix A back again. Okay. But I wouldn't recommend doing that unless you're filled with extra time at the end. Because as long as you've done the right, I mean, I could see somebody making an ERO mistake. That could happen, right? But again, in the big scope of the exam, am I going to like totally crush you on points for that if there's a mistake? Probably not. Yeah, I'm much more likely to want to see that you know how to do the problems. And this is, you know that you've demonstrated what you were supposed to demonstrate here. You might have a number that's wrong, but you're going to get a ton of partial credit even if there is a wrong number here. So I wouldn't worry about doing this unless you're done and checking your answers at the end. Okay? Is it like 250?
Yeah.
Okay, perfect. Okay, so I have one more, so the 4 topics for Math 207 are the LU factorization, the Euler method, orthogonal trajectories, and then the 4th one is abstract proofs about vector spaces. I didn't really do much of this in my 250B class, although my 250B students might be a little bit interested in this. So I'm going to, oh, this was supposed to be C, by the way, example C. So let's do one more example, call it example D. And actually, there might be a couple of examples here just to finish off with. So let's do this. So I want you guys to make sure you know the vector space axioms, right? So the 10 axioms of a vector space. You don't need to know like which one was the 4th one and the 5th one and so on, but yeah, right, because you may not have that memorized, but you need to know what the axioms are and be able to use them. So let me give you an example. Prove that the additive inverse of a vector v in capital V is unique. So this is not actually an axiom, but it is a consequence of the axiom. So for those of you just coming in, this is Math 207. So you can relax until 3 o'clock for another 10 minutes while I finish up a couple of examples with my other class here. Prove that the additive inverse of a vector is unique. So I think in class I proved that the 0 vector is unique, but I'm not sure that I ever did this one. Maybe I did, I can't remember. Does anybody have an idea how to show that something is unique? Because we did a few examples of this.
Use 2 additive inverses and show that.
Suppose there are 2 of them and show that they're the same. We did the same thing with matrices that were invertible. The inverse of a matrix is invertible. So if you have a matrix A, if you suppose there are 2 inverses, say B and C, right? We were able to show it's actually a 1-line proof that was actually part of your homework actually. You can just prove that B equals C, right? So they have to be the same. So that's kind of the idea here too. We're going to assume 2 inverses. Let me call them maybe W1 and W2. Suppose we happen to have 2 inverses for V. So what does this mean? This means that so the definition of an additive inverse is that when you add the vector to its additive inverse, you have to get 0. So v plus w1 is 0, and v plus w2 is also 0. Okay, so this is what you have to work with. And we want to show, we will show that w1 is equal to w2. So this is a good little example. I think this is part of, let me see if I can find it. I think it's theorem 4.2.7. Yeah, so if you're looking for more examples of this, by the way, guys, you can look at theorem 4.2.7. If we get done with this example and you're like, oh boy, I need to practice that some more, you can take a look at any of there's like 6 parts to this theorem, and each one of them is like a fairly short little argument that uses the axioms, kind of like this does. Okay, let me come over here. Does anybody have a suggestion what I could do next? I want to show that W1 equals W2, and these are my assumptions right here. Solomon?
You can start with W1, and it's equal to W1 plus the 0 vector, and then we can substitute.
Okay, so we could start with W1 and write it as W1 plus the 0 vector. So I'm going to, for the purposes of the thoroughness of my notes, I am going to tell you which axioms you're using. Again, you don't need to know that this is axiom 5. Axiom 5 is the one that basically tells you what the 0 vector is. It's the vector that when you add it to anything else, gives you that other vector back again. So this is just A5. Okay, but if you didn't write that and you just wrote 0 vector or something next to it, that's fine. I don't need to know what the number is. Okay, and so next you want to do what? You want to take that 0 vector and replace it with what?
Plus W2.
Okay, v plus w2, and I mean I could also replace it with v plus w1, but the whole goal here is to get the w2 represented into the solution, right? We're starting with w1 here, so I want to get the w2 involved. That's the reason for working with the second equation rather than the first one. Kind of with me so far? I mean, let me give you the outline here, guys. We're trying to end up over here. We're trying to start with W1 and get to W2. This is the whole thing we're trying to show, is that those are equal. So I'm starting with W1, I'm trying to get to W2. So we're going to take the 0 vector and replace it with V plus W2. All right. And the purpose of that is to get the W2 vector into the equation. So this would be, if I was going to justify that step, I would just say assumption. Actually, these equations here, if you wanted to give a justification here, this is A6. The definition of what the additive inverse of a vector is when you add it to the original vector, you get 0. So that's the axiom A6. Okay. Okay, so what can I do next? Change the parentheses. Exactly. And for those of you who want to know, that would be axiom A4. Okay, so changing the parentheses, I can put the W1 and the V together. This is W2 now. I don't think I have enough room here, but that's okay. I'm just going to go down now. I'll go down like this. Okay. Any idea what to do next? Can I change this to 0 yet? You know, we really should be very methodical here, since this really is a proof, to use the fact that we know that V plus W1 is 0, but we have W1 plus V. So let's switch the order, right? This would be just switching the V with the W1, right? This would be axiom. Now, if you skipped a step here, like if you just went straight to 0 plus W2, I probably would let you slide on that. As long as you're not starting to skip like most of the steps, that would be okay. But it's best to probably include it. And now you can put 0 there. Right, and so this would be, again, by the assumption. I guess that's just, yeah, from the assumption v plus w1 is just 0. Okay, and now what? Just equals this. If I want to be really, really tedious about it, I would switch these around again, because if you look at axiom A5, the 0 is actually the second vector that's being added. So this is like a mathematician being as like fussy as they could possibly be. Yeah. You know Dr. Saline?
We had him for 2 weeks.
It's funny. I used to have students who would study outside my office, and they'd want me to check their proofs, and they would come out and they wouldn't ask me, is this correct? They asked me, is this Solheim correct? Like, I'm like, would he accept it? I was like, well, it's either right or it's not, isn't it? But anyway, it was always so funny. I would accept if you went straight from here to here. If you really wanted to be so incredibly good, maybe I'd give you a little gold star. We're just switching that back around. This is axiom A3 again. And then this one is A5, the definition of the 0 vector. So this is the sort of thing. This is the absolute maximum number of steps you could ever have to think about showing. If you skipped a couple of these because you thought it was just clear, that would be fine. But you know, the most rigorous of math has to be really, you can't cheat anywhere, right? Everything has to be absolutely perfectly correct. So, okay. Does that kind of give you an idea? And like I said, there's several more practice problems you can do early on in chapter 4.2. You can take a look at some examples there, because we did do this theorem. We did a lot of the, in the Math 207, we did go through a few of those, and I even have one on the, I think the one that was on your midterm was to prove that k times the 0 vector is the 0 vector. Right, and actually that didn't go particularly well, so it might be good to go back and just kind of review a few things like that. As long as I'm not asking you to prove this, let's say you're going to use this on another problem somewhere, you can just use it. It's only if the point of the problem is to prove this statement that I need to see you actually go through it. So, yeah, so something like this one, right? You guys kind of know how to do it. You start with that side and you try to get down to 0 here, right? And the trick is, the cool trick is to just change the 0 to 0 plus 0, and then FOIL it or distribute this out, right? And then you got 1 apple on the left side, 2 apples on the right side. You use the additive inverse to cancel on both sides, and then you're left with just this equals that at that point. So that's kind of the idea behind it. So anyway, so just you don't have to, I would not spend like hours and hours like studying this type of stuff. I might ask you one question about that. So okay, so 4 topics for those of you who are here for Math 207. 4 topics. They are orthogonal trajectories, Euler's method, LU factorization, and these abstract vector space proofs. And that's really the scope of what you guys learned that's not part of the 250B. So with that, I think I'm going to turn off my camera for a minute and reset it to start a new video. Okay? Are there any questions from any of you guys about this? Okay. So just, yeah, I'm not going to probably ask you about all 4 of those things, but those are the 4 things to look at. Okay? All right, let me turn this off.